All right, I seem to be alive again, which is good. Okay, so I'm going to add a couple of very simple, we did Fezzik. Fezzik is a big, solid example. A couple of smaller ones here, and one's going to be an odd version. I've written a lot of this out. I just want to sort of walk our way through it. And the other will be just, so both two by twos. The other will have, be fairly drawable, which is a problem as soon as we get to 4 dimensions and things, but okay. All right, so this is again the subspace business, a couple of simpler examples. So we're solving AX equals B, we're thinking about column space, we're thinking about null space, we're thinking about how to escape from this, okay. We love it, we care. Okay, so what if A is just the identity matrix, right? Fine, that's a fine A, and we're thinking about AX equals B. Well, then AX equals B is always solvable. And let's just see how everything is just sitting there. So A is the identity, so identity times X is just X equals B. So given a B, the X that we need is B, right? So the identity matrix doesn't change, it just gives you back the same vector. So A times X equals B, if someone says I want to make B, we're making it with the identity matrix, then we just start with B. All right, good. So it's an odd example, but you'll see that it's an important one to think about. It's always important to think about the sort of limiting cases. Whatever it is you're talking about, it doesn't have to be math, anything. Column space. Column space, so let's just solve for it in the way we've set things up, right? So we put the A matrix here, and we put a general B in the right-hand column here in the augmented matrix B1, B2. I'm just going to solve it. It's already done. This is already, let me put this in here. This is already the reduced row echelon form already here. Right, this R sub A, reduced row echelon form, is already there. So we're done. We have pivots. That's a pivot. There's a pivot column here and a pivot column here. Perfect. All right. Okay, and so B1 and B2, they can be anything. There's no problem, right? There are no restrictions. So we just say that they are elements of the real numbers, and the nice thing to see is we can still just use the same procedure as we work through this. So we say B, we always say this, right? Always write this down. And then we replace any dependent variable with its expression in terms of independent ones. There are no such things here. So it's going to be B1, and we can just break this up, right? So B1 times a fixed vector, 1, 0, and B2 times 0, 1. So it's just the coordinate structure coming back, I hat, J hat if you like. So the column space of A, we don't have to put curly brackets or anything, we just say it's R2. It's all of 2 dimensions. All right, good. Null space. So the null space, we're solving the same setup, but instead of B1, B2, we have 0. Again, it's fully reduced already. And we just have the equations that come out are simply x1 equals 0 and x2 equals 0. Boom, right there, right? So these equations just sitting here. So the only solution is x equals 0. It's always true that the null space equation has 0 as a solution. A times 0 equals 0, which you'll be pleased to know remains true for us. So the null space for A is just 0. We'll put this one in curly brackets, just 0. So there are a couple of upshots to this that we can just to use the observations we've made so far. So because the column space of A is R2, it fills up all of R2, right? So in this case, this 2 here is M equals 2, right? This is an M by N matrix, square, so M and N are the same. So this is this statement here, because B, let's give it a different color, because every B is in the column space of A. You can't be outside of it. So, and we've figured out that means that AX equals B is solvable, right? Right. So if we take all the combinations of the columns of A, we make all of R2, therefore any B can be made, right? So that's it. I mean, dare we say, trivial situation, but it's a nice one to work through. And then, on the other hand, because the null space of A is 0, every solution is unique. Good. So many matrices there are a lot of matrices that reduce that are square, that reduce to the identity in that they have all their pivots. That's what this is. But this is one where we started with the identity. All right, so let's look at one that's a little more interesting. Well, has a different quirk. Okay. Oh, things to add here would be the dimension of column space of A equals 2, and I'm telling you that this will be, we'll see this to be R. So this is later. So I've mentioned a few times, and the dimension of the null space of A is equal to 0. It's a 0-dimensional space, no biscuits, and that we will see later on is n minus R. So both of these things are later. It's 2 minus 2. Good, juicy. All right, so different A, 1, 2, 2, 4. So the columns are clearly multiples of each other. Same with the rows. It's a symmetric matrix, which has all sorts of other good things, but that's not what we'll look at here. So let's consider two possible Ax equals B problems. B equals 2, 4, and B equals 2, 2. So the 2, 4 one we can clearly make, right? A solution might be 2, 0, 2 times the first column, 0 times the second one, or 0 times the first column, 1 times the second one. But we can tune it, and we're getting infinitely many solutions. 2, 2 we cannot make, and let's see that more clearly geometrically. We can't make it because we've only really got one direction that this A likes, right? Any multiple of 1, 2. Again, let's use our procedure so far. We have one way of finding column space. We're going to have 3, but we have 1 at the moment. That is what we'll use. There is only one true way to find null space. We set it up, A, B, right? Boom, boom, and we have a general B, B1, B2. One step of row reduction, always using our same form, right? So it's R2 prime minus R2 minus 2 here, divided by 1, right? Divided by the pivot. So we could label those things. The pivot is, right? This is always pivot 1. Pivot 1 is here. It's a very simple example. And so we're subtracting 2 of the first row from the second row. First row stays the same. Second row, we get a 0 here, a 0 here. So this, we see there's not a second pivot, essentially, right? So, and then B2 minus 2B1 over here. So this is it's fully reduced. There's nothing more we can do. I've indicated that that's the little shelf we have. This is the reduced row echelon form, right? We've got it. This is a one pivot. Let me write that. This is a pivot column and a free column. Pivot columns, we turn it. This is just the start of the identity matrix, right? That's all we can do. Right, so if there's a solution to this, then we have to have 0 equals 0. So this piece has to be 0. So that's what this statement is. B2 minus 2B1 equals 0. Just turning this around, we get B2 equals 2B1. And we're going to say that B2 is the dependent one and B1 is free, right? So this is, let me just say independent. All right, and then there's the normal sort of thing we do after that. So we'll just write it out. So B equals B1, B2. The place where we'll do this mostly is for null space, but doing the same thing. We're going to replace the B2, this dependent one, with its expression in terms of the independent one, B1. And it equals something that should be no great surprise. It's some multiple of 1, 2, where B1 is an element of the real numbers. And then column space, we have to put curly brackets around it, but this is the plan, right? So it's any multiple of 1, 2. So 1, 2, right? So any multiple of that. We'll draw a picture in a second. Find the null space of A. Now we're just going to set B to 0. We do the same row reduction. There's nothing on the right-hand side, right? We can just, if you want, if we've got this result already, we just put zeros in here, and there's our reduced row echelon form here. Okay, same thing. Pivot free, that's good. And now we use this very principled solution. We write out the equations that we have. x1 plus 2x2 equals 0. That's the only thing we have. And if we have any confusion, that's our pivot. This is our free variable. Express the pivots in terms of the free. All right? Okay. You should write that down. You should write that down. On everything. Okay. Mirrors, yeah, inside of hats. Actually, it is written there. All right, so x1 equals minus 2x2. Again, pivot in terms of the free. Yeah. And then we start off with x equals x1, x2 equals. And then we're going to replace the pivots with the free variable expressions. There it is, x2. Free variables are free variables. They don't change. We'll pull out the x2, minus 2, and 1. Where x2 is an element of the real numbers. All right, so it's this transition here. Replace pivot variable. We've got that, so let's write down, so this should make sense. So it's any multiple of minus 2, 1. And if you go back to this matrix A, right, so A times this vector basically says take minus 2 of the first column and add 1 of the second column. Clearly, that gives you a zilch. And you can have any multiple of that. So it's a subspace. This is our plan. So in sum, we have two things. We have column space of A equals all B, they live in R2, such that B equals some multiple of 1, 2. B1 is an element of R, right? This is a different thing. We express vectors up here, but this is, when we write it out like this is a box, right? I'm handing someone a box of vectors. I mean, in a sense, when I write this out. So we should have a box. It's just that there are infinitely many, so it's, oh, yeah, we could do it. All right, so, and this will be X. Again, it's an element of, it's in R2, and, oops, so X equals some multiple. I'll just keep them for consistency. I mean, we could just put C minus 2, 1. X2 is an element of the real numbers. Yeah. Yeah, so let's, good. So this is a box. Right, there's a box that someone hands you, and it has column space of A on the side, like this. I'm very excited about it. You are, admit it. Just admit it yourself, it'll make it easier. And, yeah. Okay, now we're just doodling. Okay, so this is a box of vectors. All right, so these are not trivial objects. I've drawn them on the next page, and we're going to go back and think about these solutions a little bit. Just draw, what's going on with these, right? So we know how we could solve them. Okay, so this is where X lives on the left, right? So X lives here, B lives here. So X is here. And B is here, and A sends X's across to B. So this is, so the red line on the left is the null space, right? So it's a multiple of this, minus 2, 1. So this is the null space of A. It's just a line in 2 dimensions. So let's make maybe minus 2, 1. So that would be this vector here, but we're taking every multiple, right? So every multiple of this. So the null space of A is this line. So every vector on this line gets sent to 0. So let's just take this one and we'll send it to, it gets sent to 0. Right, so A times xn for null space equals 0. So let me put this. So every vector on this line is sent to zilch, 0 by A. All right, just slays it, crushes it to bits. All right. There will be two other vector spaces, subspaces we'll get to, but these are the ones we know about so far. This character here is the column space of A, which was built out of multiples of 1, 2. Right, so any multiple of 1, 2 just traces you up and down, right? Traces you up and down here. Oop. Do that. Yeah, right. You can find any point along here. Good. Actually, maybe that's not a bad thing. Okay, so this is where you can be for null space and column space. So any vector along this line can be made. That's the story. So let me add this. So any vector here, any b in column space of A can be made by A times x, which is the same as saying AX equals B has a solution. And because the null space is not 0, so let's do that, not 0, there are infinitely many solutions. Solutions if the vector B is in the column space of A. So let's look at our two examples. We had 2, 4 and 2, 2. So 2, 4 is here. Right, so 2, 4, put it here. So this is just one example. So this is B equals 2, 4. Solvable. AX equals B is solvable. I mean, I don't know why I got carried away. So it's good, right? 2, 2 though is out here. This is 2, 2. We can't make it, right? There's no way. A can only trace out this yellow and red line. So this is 2, 2. B equals 2, 2. And maybe I should switch colors for that. Boop, 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 boop. Nearly finished this section. And then we start to get bigger again with more things. This is B equals 2, 2. And X equals 2, 2 has no solutions. Has no solutions. So sad. Sadness. But we will overcome even this great tragedy. Okay, so this is the big story we're starting to get hold of. That the X's live here. They live somewhere in Rn. It's a subspace, potentially, where they live. Okay, let me not say it like that. So there are vectors that live here that get sent to column space. There are vectors that live here that get sent to null space. So the null space vectors get sent to 0. Now I'm spinning out of control. But we'll get to that. I'm just thinking about whether I should say anything. Should I reveal anything? No. It's a secret. Okay. Yeah. We're getting close. So again, the dimensions make sense. So the dimension of null space, at least, and this is to be revealed, equals n minus r, which in this case is 2 minus 1. It's a, right, so this is a rank 1, rank r equals 1. Right, there's one pivot column. So the dimension of null space is a one-dimensional subspace. And the dimension of this column space, let me put it here, dimension of the column space of A, I'm going to claim is R, and that is again 1, right? So it's a one-dimensional thing. All right, the excitement, I know it's incredible. This is a nice little, these are good examples to think about. Sort of thing you should be able to do. The next piece is we're going to start thinking about how much information we just simply get out of the reduced row echelon form of A. And we have to talk about bases. All right, so a basis will be a set of vectors, a special set of vectors. They're not unique necessarily, right? Special set of vectors which you can use to build everything else. So like I hat and J hat in, say, R2. But of course, there will be a better basis. There'll be, I've said this before, there will be very good bases, natural ones. All right, good.